Hello everyone. So today we are going to see this a third unit. It's an unsupervised learning. So in this unsupervised learning, so we are going to see there's a topics. What is in clustering? So in this a clustering, so we have there's a two clusters. One is in K-means cluster, another one is in TB scan. So along with this a K-means cluster, we have this a clustering for the image segmentation and as well as for your semi-supervised learning. And in your TB scan, we'll having this Gaussian mixtures, anomaly detection, selecting a number of clusters, Bayesian Gaussian mixture model, anomaly and novelty detection algorithms we are going to see in this unit. So these are the topics we are going to see in the unit. Fine. So coming to this brief explanation about this each and every topic. So the first we'll start with a clustering. Okay. So coming to this clustering. So here, the clustering, here before going to the clustering, the first we need to know this unsupervised learning. Till now, we have this many machine learning algorithms which is belongs to the supervised learning algorithms. Okay, so why? Because we have this a variety of your available data. That so here coming to this, we have this a very vast majority of the available data which is unlabeled in your supervised learning. So if you have given the inputs of X futures, but we do not have any label of Y. We do not have any label of Y. So here one of the famous scientists has mentionedly said this, if the intelligence was cake, if the artificial intelligence was cake, the unsupervised would be the cake, unsupervised learning would be the cake. Coming to the supervised learning, it would be the icing on the cake. And there's a reinforcement learning would be the on the cherries on the cake. There's a reinforcement is it would be the cherry on the cake. This is the statement was given by the famous scientist. That's an Yan Liku. Okay, so this is the scientist. So now coming to the what are the topics we are going to see in your unsupervised learning? That was in cluster, anomaly detection, density estimation. So these are the three main topics we have in your unsupervised learning. We have one more thing called the association that we'll see in the next. So coming to the clustering. Here the clustering is nothing but a group of similar instances together is called as a together into we call them as a clustering. Okay. This is directly used for your data analysis, customer segmentation, recommender systems, search engines, image segmentations, and so semi-supervised learnings, dimensionality detections, and there's a more we can use in your clustering part, into your clustering part. So let us go through with the clustering part first. Let us go to this, the clustering part once. So here you can see there's a clustering part. So here the clustering has an classifications and as well as the clustering. If you see there's a left side is in classification, this one is in classification, and there's a right side one is in cluster. So if you see there's a classification, it has an required labels. Okay, three different labels. We have there's a labels here. Coming to this clustering on the right side, it can make two clusters. It can make two clusters, not three. For this from this data, this is one cluster, and this is whole as a one cluster we can make. Okay, so coming to the clustering use cases, here we already know about the classification, and there's a left cluster we have there's a labels, and there's a right cluster we have there's a unlabeled data within two subtitle clusters. Okay, So coming to the use cases of your cluster, we have some use cases. One is in customer segmentation. This customer segmentation, we have a grouping customers into an clustering. Here the examples we can say this for your marketing, adapt productions, recommendations to them. Those are comes under your customer segmentations. Data analysis, group of data into clusters and analyzing the clusters as separate. Analyze as a clusters separately. Dimensionality reduction technique. This dimensionality reduction technique, we need to be find out this which type of which cluster. Make sure this each instance is affected with each cluster or, and also we need to be replace the instances. Okay, and also this we call them as a k dimensional also. This we can call them as a k-dimensional also. This we can call them as a k-dimensional. Here we are going to be mentioning there's a finding there's a clay cluster. We are mentioning there's a cluster. Here there's a clustering, we'll call them as a k cluster. Okay. So here we need to be find out there's a cluster and there's a dimensionality reduction technique. Coming to there's anomaly detection. This anomaly detection, it's going to be cluster affinities may be useful on the as an extra feature. Okay. So here coming to this anomaly detection, it instances with low affinity to all the clusters are anomalies. So before forming as anomalies, that will be considered as an instances with low affinity. It will be considered for your anomaly detection. That will be the outer layer detection will be done first of all. Okay, lower the whatever we have that is going to be detected first. Coming to the semi-supervised learning. Here, the semi-supervised learning. So here, the data is labeled. Some data is going to be labeled, not total data. Some data is labeled from the cluster and propagates the label to all the instances in the same cluster. Okay, it has from the clusters and propagates the labels to all the instances in the same cluster. Okay, so coming to this, the future engineers. The future engineering. So what happens here for this engines and this segmentation as an image? We are going to be clustering affiliated with many useful as an extra features. Many useful extra features we are going to be added here. Okay, we'll see this. What are the extra features and how it is going to be seen as a further classes. Okay, so now coming to this. The search engines, it's going to be refers as a images that may be a cluster images. Returning there's a matching the clusters also will be done. Coming to the segmentation of an image, it's going to be cluster the pixels by a color. It clusters as a pixel by a color it's going to be mentioned. It searches for the similar images to be referencing images, and also cluster images returns to the matching cluster. Okay, so these are the some use cases for your cluster. Okay, so I hope the topic was clear regarding the clustering and unsupervised learning. Okay, so now come back to the K-means algorithm. Okay, so here we have there's a two clustering algorithms, K-means algorithm and DB-scan algorithm. Hierarchical clustering is also we have that will be learned in the further classes. Okay, so K-means clustering. Here it was proposed by Bell Labs. It is proposed by Bell Labs by 1957. Bell Labs 1957. The data has in 5 Gaussian blobs that we call them as a Gaussian blobs. This Gaussian blobs will be takes place in their clustering. Okay, so coming to those decision boundaries. This is a decision boundaries. Coming to the decision boundaries, here we are going to be minimize as a decisions to the centroids. These are the centroids which I place as a pointing here. This is the here I'll place. This is a centroid. Okay, so it's going to be coverages to the good solution when the blob or all have the same size. Have the same size. Here we need to note that here it's near at the top left decision boundaries. Top left decision to the boundaries. So to be find out this, we have there's a two clustering formats. One is in hardware cluster, another one is in software cluster. It is going to be soft hardware cluster. It's going to be assigning each instance to a single cluster. The soft clustering, it gives us each instances a score per cluster. A score, it's going to be give some score, such as a distance to the centroid will say that. A distance to the centroid will say that. Already I have told you this, these are the clusters is a Gaussian blobs. Gaussian blobs. Here, this finding as a distance that we score identifies by using a Gaussian radial bias function. Thus, what is this a function is a transform method. By using this a transform method, it's going to be find out this a distance and the dimensionality reduction for the clusterings what we have seen now. Okay, so come. So let us see this. There's a K means transforms. The original data was in two-dimensional data. Two-dimensional data. So what was the original data? That is in x1 and x2. That's a dimensionality data. This is an x1 and x2. Okay. So when we are forming this x1 and x2, we need to replace with 5-dimensional data with distance of each instances to the centroids. Each instances to the centroids. So what happens whenever we are performing in that way? If the original data has a high dimensionality, a method of dimensionality reduction will be performed here. So if you see this, already I have told you this, by using a transform method, you are going to get this distance. Okay. So if we find out this, we got this distance of the each and every instances. Okay, each and every instances. It's going to be labeling. There's a random placing. There's a centroids. We can see this random placing to the centroids and labeling as the instances to find as the nearest centroids and update the centroids to the instances in that particular class. And again, we need to go for this step back. So let me recall this by using an how does the K-means algorithm work. Here there's a working of the K-means algorithm. The first we need to select the number of K to decide there's a number of clusters. So there's a second one. Select the random K points or centroids. It can be other from the input data set and assign each point to the closest centroid, which will be predefined by using a clay clusters. Okay, which will be for the predefined K clusters. And we need to calculate the variance. We need to calculate the variance and the place in new centroid of the each cluster. Variance and place in new centroid of an each clustering we are going to do. Okay, and also we need to repeat the third step. Again, we need to repeat this third step, which means reassigning each data point to a new closest centroid of an each cluster. Okay, so which means we have to reassign this each data points to the nearest closest centroid of the cluster. Okay, which nearest closest cluster it has to be pointing out. Okay, if any reassignment occurs, then go to the step 4, else go to the finish. Okay, again we need to be calculate to the variance and there's a place near to the centroid of the each cluster. Okay, and we need to go for this finish. Now there's a model is going to be ready. Okay, so now you see this diagram. There's an algorithm. So the first step, what is the first step? So we need to know there's a number of clay clusters, random points, and we need to assign this data points to the each and every closest centroid, and we need to calculate the variance and there's a new centroid of the each cluster. Okay, so this is the first one. We have given there's a random centroid, random clustering along with the centroids, and again we have find out this the variance and the data points we have seen. So by performing this step 3 and this step 4, So finally we got this type of clustering format. Okay, this type of clustering format. So we cannot able to say this here. It scores the sum of the squared distances from the centroid, and the positive score is called as an interior. Okay, the positive score is called as an interior. So coming to here, it may have as a suboptional solution. Why? Because we have this, it's not a correct solution. We can identify this. Here we can see close to this optionally for this clustering for the three iterations. So now coming to this suboptional cluster or solutions. So by the bad luck with the initial centroids, it tries n in its differentiation to starting as a location, from starting locations to here. Okay, so here we are going to be see this the computational complexity here to find out this. Okay, computational complexity. To be find outing there's a computational complexities. So we have to go through with an the performance metrics that we call them as a modern models. It in a It's called as a model retina, which may have the mean square distance between the each two instances and which is the closest to the centroid. When you are performing these optional instances, optional suboptional solutions for this complexity, computational complexity. So it's roughly equal to the first three solutions we got. Solution 1, it's roughly equal to 2.23, and the left one is 2.37 with different random initiations. And this coming to this third one is in 2.11 for this model. So whichever we got this optional optimal model, so that model is going to be considered as the correct or best outfit model to the particular algorithm. Okay, so this is the median means decision boundary for your clustering. Okay, I hope it is clear up to here. And also here we are going to see this one more point that he said. So how can we see this? The 211 model is going to be as a best solution. So here for the improvement of your k means, we have this a k plus a means plus plus algorithm also. This has an improvement proposed in 2016, and it's going to choose us as a better starting centroids that are more distance from each other, that are more distance from each other, and also it has as a much likely to coverage converge to a suboptional solution. And also defaultly the method is also called as a k-means class, but we are using it. The default method for the k-means is a class we are using. Okay. So coming to this, we have this many implementations. So let us see this. The first one is an accelerated and mini batch k-means. So what we'll do here means on large data set with many clusters, the calculation can be accelerated. Okay, and also we can use as a triangle inequality to estimate distance using upper and lower boundaries. And also it doesn't work also always. We can make training a little bit slower to the particular person. Particular person. Okay. Here it has a large data set and with many clusters, and the calculations may be accurate, and also we can using this triangle inequality to estimate the distances using an upper and lower bounds. Using an upper and lower bound does not always work. It can make training slow. Okay, training slower. So and along with us coming to this a mini batch k-means. So here in this mini batch k-means, we are using only a part of the data of each iteration. Okay, part of the data of each iteration. Okay, it's moving as a centroid just slightly each time. It's moving as a centroid just slightly to the each time, and also speed ups as algorithm, and also it allows us a use of huge data set, and also it allows with a huge data set now. Okay, so here below you can see there's a two graphical representation. One is in k-means, another one is a mini batch k-means. So what happens? We are going to be slightly with us moving with us centroids each other. And also there's a training seconds will be have there's a differentiate k-means and along with there's a mini batch k-means. It's going to be differentiating between the centroids. It's most likely to near to it. Which are the near to it? It's going to be mentioned. So coming to this the next one, have to choose as a k. Here we are mentioning this. It's moving centroid to the slightly each time, and we have there's a data for each iteration. Okay, so now we choose as a k. Have to choose as a k. We have to choosing as a k. More clusters means lower inita. Okay, so more clusters means lower inita. It's going to be mentioned even if it is outfitting the data. Even if it is outfitting the data. So here we'll take the three clusters. We'll take here the right side we will take this 8 clusters. Okay, so I'll take this three clusters. I'll take one more 8 clusters. Okay, so there's a initer is going to be drawn. There's a clustering. How many data points is going to be adding here? Okay, there's a data criteria constants is going to be happening here. So when you are performing with this three clusters, it's very neat. We have this only at three clusters. If we come to this 8 clusters, each and every any data point is going to be differentiated. At the time when it is going to be point outing from higher 1 point, 2 point, there's a elbow is going to be started. There's a mini is going to be coming down, initially randomly initiating, it's slowly downing into it. Okay, so from this, so we have to go with the shell shot score. Okay, fine. So coming to the scoring part. Okay, so coming to the scoring part here, this is scoring for the each instances. We are going to be scoring with the each instances, that is a b minus e by maximum of a comma b. So here we have this, we have told you there's a x and y coordinators, x2 minus x1 coordinated by maximum of x1 to x2 coordinators, it's going to be tick. So here you can see there's a it's going to be mentioned as a main distance to the other instances in the same cluster. A is a mean distance, it's a near to the distance to the other instances. B is a mean distance to the instances in the next closest cluster. Next closest cluster. Okay, and also here it varies from -1 to 1. If it is having there's a +1, if an instance is well inside its own cluster and far away from the cluster. Its own cluster and far from the other clusters we are going to be take. Coming to the -1, if you got any varies from the -1, if an instance is assigned to the wrong cluster. Okay, so this means coefficient over this all the instances is going to be performing. 2 varies as a from -1 to the 1. So now we'll see there's a result for this each clusters, 5 cluster and as well as the remaining clusters. Okay, so here the result of your 5 clustering data 2, 4, 5 and there's a 8. 8 clusters we have taken. 2, 3, 4, 5, 6, 7 and 8 clusters we have took. Here, there's a fourth one is the best choice. For that's a clustering part. But there's a fifth is a second best one. Fifth is a second best one. Okay, so 1 minute. Fifth is a second best choice for the cluster. Okay, this is a result we have got with the variance -1 to +1. Okay, so this is the variance of the scoring of the each and every cluster. Okay, so now coming to this, what are the limitations for your k-means? It is a pure behavior when the clusters have the varying the sizes, different densities, or non-spherical spaces, non-spherical spaces, and also here we have the Gaussian mixture or the better for these elliptical clusters. Okay, so Gaussian mixture or the better for this elliptical clusters. Why? Because you can see there's a inhibitor versus 242.6, higher 2179.5. So based upon this, we have to be do the clusters for your limitations. Okay, so this is the limitations for your k-means. Okay, so this is the whole topic for your k-means clustering. Okay, so coming to the next class, we are going to see there's a Gaussian mixture and there's an image segmentation using as a cluster and semi-supervised learning using as a cluster. Okay, so I hope this topic was clear. There's a k-means cluster. Okay, so please go through the topic. If you have any doubts, you can raise your voice. Okay, thank you so much.